So what I'm going to tell you about might seem a little bit exotic to some of you, but also might seem quite relevant to hopefully the same people. It has to do with molecules rotating in quantum solvents. So the problem that we are in principle trying to tackle in general is a very broad one. So all of you know that angular momentum is quite tricky in quantum mechanics, right? So if you open a book, whatever you like Landau-Lifshitz, right? Of course, like if you open Landau-Lifshitz and you read about translational motion, right? There is Heisenberg uncertainty principle. It is very different from classical mechanics, but in a few paragraphs you can understand what's going on. The thing is that translations, well, they don't commute between momentum and position, but different translations commute with each other, right? So if you move that way, or that way, you get the same result. If you do rotations, they do not commute, right? So if you rotate about two axes in different order, you get different results. Therefore, they're described by so-called non-abelian algebra, right? And as you know from quantum mechanics, to add two angular momenta in a simple atom, you need a Clebsch-Gordan coefficient, right? If you want to add 3, you need a 6J symbol. If you need to add, a 4, you will need 9J symbol. And some people in atomic physics, like Chris Green, for example, they know how to work with 72J symbols and such. But what can one do if you really have a lot of particles? So a lot meaning like an Avogadro number of particles. So is such a problem fundamentally solvable at all? And this problem is not just of mathematical interest. So it arises in a number of very important situations both in chemistry and physics. So for example, in chemistry, molecules rotate, right? And the way they approach one another determines the reaction rate, with what ends they hit one another during a reaction. And usually reactions take place in solvents or on surfaces. It's like, heterogeneous catalysis is usually on surfaces, and they exchange angular momentum and therefore, rotation with some kind of bath. And understanding how it happens is needed to control chemical reactions. In solids, it's like many of you have a background with solids, electrons exchange angular momentum with phonons, right? And from spin to orbital angular momentum to the angular momentum of phonons. So this is related to the problems that people are trying to tackle in ultrafast magnetism, in spintronics, and also quantum computation in terms of decoherence of spin qubits. And for that, we need to understand how angular momentum is distributed in many particle systems. And I'm going to talk a little bit in more detail about that as well. So that was kind of a big picture that we drew for ourselves, but of course what triggered us initially to think about these problems were particular experiments. And these experiments don't even really belong to physics, they even belong to physical chemistry. So namely what people do, and that's quite a large community, they trap individual molecules in tiny droplets of superfluid helium-4. The reason they do it is to study molecules. So they want to isolate molecules in such cold environment where they're not moving fast, they're not colliding with other species, so they can just record very nice clean spectra and also prevent some unstable species like some free radicals from reacting in a gas phase. So this is quite a mature field. So what people knew and what people observed for 25 years was that if you take a molecule and you measure its spectrum, so in this case it's like a vibrational spectrum, but we can focus on rotations as well. So you measure a spectrum of a free molecule, then you put it in superfluid helium-4, and what you observe is pretty much the same spectrum, but it is kind of shrunk. So the spacing between the lines changes. What it means is that if you have, a simple linear rigid rotor, right, like it's a rotating stick, the spacing between the rotational lines changes, which means that the stick starts rotating slower in a solvent. So it acquires some effective moment of inertia, right, similar to Polarons and effective mass, right? That was not obvious. This last sentence was actually not kind of obvious 20 years ago. And so people were interested mostly in kind of molecules. And so what they were doing, they were collecting the spectra, trying to fit it with some renormalized moment of inertia, like some effective type of mass, and studying molecular properties. And they were not that much interested in details of interactions of many-body interactions between the solvent and the molecules, to large extent. That changed recently, in around 2012, 2013, when Henrik Stapelfeld, who some of you know, measured dynamics of such molecules in helium. So dynamics in this case means that the molecules are struck with a very short laser pulse, and there is a rotational wave packet that evolves in time. So you can imagine that you have a molecule, again, like a stick, right? It's rotating. Then if you apply a laser field, which is linearly polarized, this stick will tend to align with the polarization of this laser field. Now, if you switch the field on and off adiabatically, adiabatically means it is slower than the rotational time scale, right? The rotational period. So you switch it on, your stick aligns, and then you switch it off, and the molecule keeps rotating. What happens now if you switch it on and off non-adiabatically, if it's a very short femtosecond or picosecond pulse? Then you create a rotational wave packet which is going to undergo revivals. So this black curve is what people observed in the gas phase for free molecules. And again, that was, on the other hand as well, a mature field. So you have like a delta-shaped pulse here, and then the molecule is aligned. So this shows how much the axis is pointing along the polarization direction, and you see the revivals after the pulse is gone. And here you see it's a zoom in into the situation. So how many of you like spins more than molecules? I mean, don't be shy. I know most of you don't like molecules at all. I mean, so for spins, it's exactly the same situation. So imagine like if you have spin up, right? And what they kind of do is, they apply pi over 2 pulse to create a superposition, and then they measure this sigma x projection, right? And then if you measure it, the spin is going to precess and oscillate, right? And that's exactly what they measure, and they would obtain exactly the same sinusoidal curve if they mixed only 2 rotational states. Here they mix like tens or sometimes even hundreds of rotational states. That's why these peaks are extremely narrow, because only at some particular moment of time all phases of your wave packet come together, right, to revive. Anyway, again, from a chemistry perspective, Henrik Stapelfeld wanted to try to understand what's going on if you try to do the same experiments in solvents. And helium is quite a nice model solvent. So what people would expect is that if in spectroscopy you observe that nothing changes, but the distance between the levels, right? The energy splitting between the levels, here you would expect that you would observe the same type of dynamics with different spacing between the revivals, right? However, what they observed is completely different. So they observed this red curve, so it's here or zoomed in here. And what's interesting about this curve, it's not only that there is no revivals and it's kind of decays, but some new long time scale emerges here as well. So it's not like you observe some peak here and exponential decay as if it would be in some kind of Markovian bath, but here the maximum of this curve emerges at much longer time scale. So it's 1 or 2 orders of magnitude longer than here. So something qualitatively different starts happening. So good news for us was that the static problem, just the spectra of molecules in helium were explained quite well with Monte Carlo simulations, also with DFT and various numerical approaches. But if you try to do such type of dynamics calculation, it's extremely challenging to do numerically because it's many-body, quantum, and also far from equilibrium. So we took it as an opportunity and decided to approach it from the a point of view of impurity problems, right? So like a Polaron problem. So in this case, we have exactly 1 particle per droplet, so it's kind of a textbook impurity problem. And the idea that we had was kind of obvious, but and then should have been formulated probably 20 years earlier. But the idea is that, if we have an electron or an ultracold atom in some bath that acquires an effective mass through translational motion, Here we observe a situation where a rotating molecule acquires an effective moment of inertia. So by analogy with polarons, we must have some kind of quasi-particle description. And of course, it's extremely important before starting to do any actual work to come up with a cool name. So we called it Anguilon because roton was taken by Landau. It had nothing to do with rotation in the end. And then after you come up with a cool name, you of course Google, and it turns out that there is like a list of quasi-particles in Wikipedia. And most of them were introduced in the context of condensed matter, and actually they are described in terms of linear momentum or topology sometimes, of course energy. But it turns out that there was no quasi-particle description of any angular momentum processes. And most impurities in condensed matter are just spins, and often spin 1/2. So before I show you some actual results, I just want to get back to like a big picture and tell you that we started working on it with the following picture in mind, that we would like to understand molecules in helium. However, the theory can be applied to in pretty much any impurity that has angular momentum and interacts with, in principle, any kind of bath, which could be electrons, and we also applied it to the Einstein-de Haas effect. I'm going to talk about it if I have time. Then it could be also, organic and inorganic perovskites that have molecules rotating in them, or like Rydberg atoms in ultracold gases, or any other problems. So I'm not going to show you too many equations, and I'll be happy to discuss it after my talk. But I can give you an example of the simplest Anguilon Hamiltonian that describes such an impurity problem. So it's probably one of the simplest versions. So here you have a molecule, molecular Hamiltonian, which is just a rigid rotor Hamiltonian. Could also be something more complicated. Then there are phonons that have some dispersion relation. And here we describe phonons in terms of their angular momentum. So instead of B-Dagger-B operators working in plane waves, phonons along x, y, or z directions, we expand phonons in the spherical basis. So we have like spherical, S-wave, P-wave phonons, D-wave phonons. And so it's just a basis transformation. Here, nothing new, but what goes beyond textbook is some kind of coupling of that form. So of course, many of you, in particular in the field of Polarons and also in quantum optics, have seen at least maybe 57 Hamiltonians that have some kind of B-Dagger plus B coupling. So the difference here is that you have a coupling to continuous variable, so similar to the Froelich Hamiltonian, but this variable is on a sphere, right? So that induces all non-abelian type of algebra that makes the problem quite different from what has been studied in Polarons, for example. So this Hamiltonian was derived exactly for a molecule in a weakly interacting BEC, but I'm going to argue that it can be used as a phenomenological model for more complicated systems like molecules in helium and maybe other systems. And yeah, the initial work has been done with Richard Schmidt, who is going to give a talk tomorrow, I guess. So don't miss his talk. He's probably going to talk about other things mostly. And so this is what we call the anguilon. So like a polaron is, some particle dressed by a cloud of excitations, kind of exchanging momentum with it. Here we call the anguilon a particle that exchanges angular momentum with some kind of bath and is dressed by some angular type of excitations. And to give you an example, so this is just a tiny part of the results that I'm going to show you. So it's just only some of them were obtained using this ansatz, but many of you know the so-called Chevy ansatz, where you have single bath excitations, right? And it's very similar to Polarons, but there are differences. So for example, so you have an unperturbed wave function, right? So you have no bosons and molecule in some state Lm, which gives the total angular momentum, and then you excite one boson, right? So you excite a boson with angular momentum lambda mu, you change the molecular state, and then, in Polarons, to conserve linear momentum, you would write, P, Q, P minus Q, right? Here, to conserve angular momentum, you need Eclipse-Gordon coefficient. And so if you excite two bosons, you would have like 6J symbol and so on, so life becomes quite complicated very quickly, but also quite interesting. So, skipping a lot of equations, I would like to show you some results. So after we, wrote down the model, we developed a few theoretical approaches to studying strong coupling regime, weak coupling regime, and so on. But a crucial step was to actually show that the ideas were not nonsense, right? Because we can theorize about many things, and then what works in practice is another question. And for us, we're collaborating with people from the helium droplet community is kind of a gift in this case, because the field is quite mature. So there is 25 years of published data that has been analyzed from the perspective of molecules. So people were asking their own chemistry questions, and now we can pretty much go through all this data and analyze it from the perspective of quasiparticles. So we don't need to convince some ultracold atom experiments to take our proposal instead of someone else's and so on. So there is a lot of data that we could use to benchmark our theory. So in this case, this is data on like 20-something molecules. This is the ratio of rotational constants of these molecules. So it shows how much slower these molecules rotate in helium compared to the free case. There are molecules that are very heavy, so their kinetic energy is small, and the effects are therefore very large. The potential energy is comparatively large. So the effects, as you can see, are quite substantial. So some of them rotate like 5 times as slow, like 3 times as slow compared to the gas phase. Some molecules are extremely light, like water, ammonia, methane. And note the scale, so it's 90% to 100. The effects are on the order of a few percent. And there are some molecules in the middle that are, either or, so they can be weak coupling, strong coupling, or require some of their own theory. So here is our theory. And first of all, we developed a theory for the weak coupling, also with Richard. And so you can see that, okay, you can see the agreement is not perfect, but this difference is actually like 1% or so. So we would say the agreement is quite satisfactory for these molecules. And one fact that I would like to mention about this weak coupling regime is that if you have a simple theory at hand, you can connect different fields and see kind of parallels between different research directions. For example, here it turned out that the effect of helium on these molecules, so the fact that their moment of inertia changes by a few percent, is exactly the same effect as lamp shift in hydrogen. So you remember in hydrogen you have one S state, and then 2p and 2s states are degenerate quantum mechanically, but then they split because of the effects of quantum electrodynamics, right? So they split because they're addressed by virtual photon excitations from the vacuum. Here you have an exactly same effect, but you have phonons instead of photons, and rotational angular momentum instead of electron angular momentum. So you have different shifts of rotational states because of different dressing by phonons from helium. And I mean, probably no one cares, but I think it's kind of cool if you can connect on chemistry with quantum electrodynamics. Maybe we can understand things better. Then we also developed a strong coupling theory where we eventually needed to kind of add an infinite number of angular momenta, and I'll be happy to tell you more concrete details in the break. But it describes the theory the experiment, quite reasonable as well. And yeah, and then for the intermediate coupling regime, what we observed is that strong coupling theory is also like describing things quite well, or here weak coupling theory. But to be honest, like we need an intermediate coupling theory that also Giacomo is going to tell you about in the next talk. And here the green dots show some very preliminary attempts to do it. But quite importantly, what I personally find quite important is that many of these points. So it's a static problem, right? It's not far from equilibrium dynamics yet, but many of these points could be, or actually have been obtained using Monte Carlo computations or DFT or such numerical techniques. So the difference here is that we have extremely simple equations that describe the renormalization of the rotational constants in the weak coupling and strong coupling regimes. And so here we did, we aimed for the simplest possible model. So what we took here as an input is this delta, which is the anisotropy of molecule helium potential. So we take it from the literature. It's pretty much if you have a molecule and helium, so it's interaction that way minus interaction that way. And there are phenomenological parameters. So in this case, this psi describes all blue points. Of course, it's the same for all the blue points, and this eta describes all the red points. So we think that it might be possible to extract these parameters also from some ab initio computations, and it would be nice to talk about it with the experts. But already, you know, if we have one parameter for like 15 points, it's probably not that shameful. So that provided us with some evidence that, you know, our theory is not a complete nonsense, and molecules in helium probably can be described as these angular quasiparticles. We were kind of new to the community, and we kept talking to people. And it turned out that the statement that I made in the very beginning, that, you know, you put molecule in helium and all lines remain sharp, but they shift, right? So it turns out to be true, but, you know, not always. So it turns out that, for example, for methyl radical, so you have a gas phase spectrum, and you put it in droplets, and you see all lines remain sharp. And so as I showed here, the change of the spectral lines is like 2%. So it's negligible, the positions. But one of the lines becomes extremely broadened, so by 50 gigahertz or so. And then, well, people published it in 2013, and they didn't know, like, you know, what it could be. Of course, it was obvious that it's some kind of effect of helium and some kind of transfer, probably, of rotational angular momentum. And then Gary Doberly approached me at one of the conferences, and he was wondering whether this effect that they measured in 2013 was the same effect as we actually predicted 2 years later without knowing of that measurement. So we predicted that at some coupling, at some critical coupling strength between the molecule and helium, these angular quasiparticles can decay and emit angular momentum into the bath. So we found it interesting because before, when people think about angular momentum and superfluids, people would think about vortices, right? And to create a vortex, you need to transfer one angular momentum unit per particle of the superfluid. And in this case, we can transfer like 1 or 2 or 3 angular momentum units per all particles. So it's some kind of different mechanism of angular momentum disposal. And well, that was the question he asked, whether it's actually related. And then student, PhD student in my group, Igor Cherepanov, he looked at it, and he found out that it seems to be the case. So indeed, if you take methyl radical and you calculate the spectrum, it turns out that the interplay between the rotation and the interactions with helium is such that this line becomes very broadened through transfer of angular momentum. So it's 3 units of angular momentum are transferred here. He also found some other data for ammonia, which is like a bit noisier because it's a bit older, but still it's a similar molecule, similar spectrum, and he also observed this broadening. So then what is also useful, to have a simple model for is that you can play with it and try to predict some physics that can be maybe measured later in experiments. So a postdoc of mine, Andrea Alpiacoboilo, he's more interested in mathematical aspects and like gauge fields, and he has shown that molecule rotating in helium or in a helium droplet can be seen as a particle on a sphere in the center of which there is a non-abelian magnetic monopole. So that sounds very exotic, and it is kind of exotic, but the idea is qualitatively simple. So for example, you know that rotation and magnetic field are similar to each other, right? So if you have a superfluid, you rotate it, you get vortices. If you have a superconductor, you apply a magnetic field, you have vortices. And in this sense, if you have a molecule which rotates in a superfluid, you can imagine that in the frame of reference of the molecule, the superfluid rotates. And then it interacts with the molecule and induces some kind of field. And that was shown to be the field of a monopole here. And also this monopole is non-abelian because the field carries angular momentum, which is non-abelian, so they don't commute with one another. And well, he has shown that there is some topological transition and these instabilities that we believe have been measured. On the previous slide, I've shown some of it. But yeah, the topology directly has not been measured yet, so we're thinking how to measure it. So let me show you some, some of the results connected to my first question, so to the question that actually triggered us to start with that, namely far from equilibrium dynamics of molecules in helium. So this is one of the data sets that Henrik Stapelfeld collected recently. He collected a lot of data, but this one is probably one of the most exciting. And the situation goes as follows. So if you have a molecule in the gas phase, right, you apply a very short pulse, and then you observe rotational revivals, right? So like in this case, you have an iodine molecule, it gets aligned with a very short pulse, and then you observe revivals at like 250, 500 picoseconds, and so on. These structures also change. As you can see, there is more fine structure depending on the intensity. So if you change the intensity by 1 order of magnitude, there is not much structure in between, and so on. So there are very characteristic features of these alignment traces. Now, he was extremely surprised after he has measured the same molecule in helium droplets, because you can see that you put it in a droplet and you change the intensity by 1 order of magnitude, and you do not see much change in the alignment. On the other hand, it's not like you just observe nothing, right? Like it just decays due to the bath, and that's it. No coherence preserved. You clearly see coherent oscillations as if it was some kind of spin 1/2 problem, right? Some kind of precession between two levels, right? They change a little bit, but not much. But this is a huge change in intensity. So believe me, it should change, like everything should change, but it doesn't, right? Then he did the same experiment with CS2, and he observed as well that you change it by more than 2 orders of magnitude, or by more than 1 order of magnitude, maybe like 1.5, and you observe these persistent oscillations that grow and then decrease, but they don't change that much, like not comparable to how it would change in the gas phase. And similar for OCS, so it's a noisier spectrum, but still you see some oscillations here and so on, but you see less of them. So we used our simple model to try to understand what's going on. It turns out that there are two effects, actually, the structural and dynamical. So first of all, a natural thing to do is to take a Fourier transform of these time-dependent traces that I've shown you to see what frequency contributions are there, right? And you can see the blue lines so showing the frequency contributions to the spectra of molecules at some particular intensities. And what we observe is that there is a huge peak here, right? So there is a clustering of frequency, which is really weird, right? Because if you have a rigid rotor, the spectrum is quadratic, so the splittings grow linearly, right? So there is no clustering. From our theory, however, it follows the same, that actually the spectrum of molecules in helium is modified drastically. So it's not just some kind of effective mass, right? Not effective moment of inertia in this case. It's something way more complicated. So it's not just that some low energy behavior changes and it's uniform, but the spectrum really becomes equidistant here. And therefore, you have a lot of levels that whose spacings cluster around this frequency. So basically, due to the environment, the rigid rotor starts behaving as some kind of harmonic oscillator, right? So it has like a lot of equidistant lines that coherently oscillate. So for CS2, this effect is weaker, and you see that this peak is weaker, and it also disappears at some higher intensities, as we can see. So basically, this is also explained by the theory because the number of these levels is just smaller. And then for OCS, there is some peak, but this effect is much weaker. The question is, then, is this structural change sufficient to describe the experiment? So if we take like an imaginary molecule with such kind of spectrum and make a gas phase calculation with it, right, without any dynamical effects of the bath, would it be sufficient? It turns out that no. So in here you can see that the comparison with experiment, so experiment is the black line, the theory is red line, is not that convincing. So you can see that it's not that not all the features are described. So it turns out that the second effect that is extremely important is to dynamically populate these levels. It's not enough to have these levels in helium. You also need to populate them, as opposed to levels higher or levels lower. You need to somehow confine your population there. And that's what happens due to the picosecond transfer of angular momentum between helium and the molecule. And here we see the different populations. So it takes place at a time scale of like 10 picoseconds. And this is sufficient to observe these oscillations. And I would like to show you the comparison. So we have this experimental data. And here is our theory. And so we can see that, so for iodine, like the agreement is quite substantial. And then here the agreement is quite good as well, I would say. And then even here, like in these experiments, sometimes you don't know what's noise, what's not. And then we can clearly see that these effects are some oscillations, right? And they're not noise. So you see like these features, they are clearly reproduced by the theory, although, they might look like noise. Yeah, and that was done by Giacomo and Igor, and Giacomo is going to talk about something else in the next talk. And what we're working on now is also like more sophisticated techniques like truncated pulses, and we're also trying to describe it, and optical centrifuge that allows to spin molecules up to like, hundreds or thousands of angular momenta, and maybe when one can produce a vortex like that or something of that sort. How much time do I have actually? Okay, perfect. So I would like to switch gears a little bit and tell you a little bit about this broad picture of angular momentum in condensed matter systems, and namely, I would like to bring your attention to this problem of electron-phonon coupling and exchange of angular momentum in such process, right? So all these experiments, or like all the ideas of exchange of angular momentum between electrons and the lattice go back to the famous experiment by Einstein and De Haas. So they put a chunk of material in the magnetic field, and after they switched the magnetic field, they observed mechanical rotation. Then Barnett did a reverse experiment where he rotated a chunk of ferromagnet, I think, and then it developed polarization. Back then, it was extremely cool, and I mean, actually, it was a bit misinterpreted by Einstein and De Haas. It was called some molecular currents and so on, but ultimately, it allowed to understand what spin was, right? Because people had no idea that spin was angular momentum, and here, you would conclude that it makes sense, right? That you change the angular momentum in one subsystem, in the magnetic subsystem, and you acquire angular momentum in the mechanical subsystem. And it actually made sense for the most of the 20th century, and people didn't think about it that much until quite recently, where experimental advances allowed to study magnetization at femtosecond time scales and at nanoscale, like develop some nanomagnetомechanics or do spintronics or ultrafast magnetism, for example. So in ultrafast magnetism, what people want is like as usual. Namely, the goal of condensed matter physics is, to make your iPhone better, right? And they want to switch magnetic moments with very fast laser pulses as opposed to slow magnetic fields. And what they observe, and if they induce magnetization, it disappears after some time that is too short for any theory to understand it, right? And people for 20 years are trying to understand, like, where does the angular momentum go? Like, what is the angular momentum of phonons? And, how to describe it at the microscopic scale? And things of that sort. So the philosophy that we have here is a little bit along this, quantum simulation line, although, we don't call our activities that way. But the idea is that, we have this system which is quite controllable. It's not as controllable as ultracold gases, but on the other hand, it features quite strong interactions, right? So it is a bit more complicated to understand, but it's still possible to understand molecules and helium. And then there is a system that is much harder to understand. It's, electrons in solids, right? And what we would like to do is like to write some kind of universal Hamiltonians that would, in principle, allow to understand the basics and maybe to draw the parallels between, rotational angular momentum and orbital angular momentum. How it gets transferred to excitations in a superfluid or to lattice phonons, because, the fundamentals are not that different, right? Although these communities pretty much don't know of each other's existence, probably. And I would like to flash some kind of results that we obtained. So in a similar way to molecules in superfluids, we introduced angulons to describe electrons in solids. It's just our first very rough paper. So the idea is that instead of a molecule, you have many electron Hubbard impurity. It is coupled to lattice phonons instead of vibrations of a superfluid. But the idea is quite similar. So, of course, the Hamiltonian for this, multi-electron Hubbard impurity is much more complicated compared to the Hamiltonian of a rotating stick. But, considering it dressed by phonons, it also makes it, look like the same kind of angular. And we can study it, right? And then we can try to understand what's similar and what's different. So for example, for molecules, what you're interested is some kind of mechanical response, right? Like if you rotate it mechanically, you observe that the moment of inertia changes. For electrons, it's different. They're not mechanical that much, but what you can try to understand is how the response to the magnetic field changes. So the lambda G factor. And lambda G factor is kind of moment of inertia for electrons, one could think of it in that way. So for example, here we observe that with electron-photon coupling, with growing electron-photon coupling, the lambda G factor increases in a similar way as the moment of inertia for molecules increases. And, well, we predicted some other effects, but anyway, what I would like to briefly mention here is that Gary Doberly had some unpublished data on OH molecules and helium droplets, and these molecules have spin. So they have also like spin rotational coupling and rotation couples to phonons and so on, very similar to these electrons and solids. And for these molecules, he observes exactly the same effect qualitatively, that the lambda G factor increases in the presence of a superfluid. And that gives us hope that we can maybe draw these parallels between solids and molecular physics and try to make sense of it. Okay, so I'm pretty much through my talk. So what I wanted to tell you is that we are making a kind of strong statement that if you have something with angular momentum coupled to some many-body system, it might be possible to simplify it using this angular concept. We have shown that it seems to work for molecules in superfluids. Of course, there is a lot of work to be done there as well. And we are pursuing several different directions. So we're studying the model itself because, as you know, like even Froelich-Polaron model is not that easy to study here. It might be even more complicated than the Froelich-Polaron. And there are extensions beyond Froelich. And we're trying to develop different techniques like path integral and diagrammatic Monte Carlo. And Giacomo Biggin is going to give the next talk about it. And there are results on B-angulons and moving angulons. And we're trying to apply it to various fields like chemical reaction dynamics and also perovskites. And yeah, if you have any ideas why it could be useful, let's talk. It would be very exciting. So that's the group collaborators. Thank you very much. So it's an excellent question. So in this case, these droplets are pretty large. So they're like around 1 million or so atoms. And in this case, it seems that the surface modes are not that important, or like the cavity mode, so to speak. People can change the size of these droplets, but there was not so much. It was not so systematically investigated, I would say. So what we wanted, the statement we wanted to make here is actually to take the bulk limit because, very small systems can be studied with Monte Carlo, for example. You can take, 100, 150, maybe 200 atoms, and with DFT you can take more. But then, for large droplets, it is pretty much impossible to do numerically, right? But it's an excellent question, so we would like to look into that as well. So in principle,
because they form two-dimensional gas located near the surface, and their edge distance, the radial edge distance is very large. So they, in fact, are described by angular variables.
Yeah. One of the referees asked exactly the same question a few years ago. But he might be, or she might be here. Anyway, but in principle, yes. So we didn't look into it because, again, what we wanted to do is also to take some field studies very systematically, experimentally, because it's very easy to see here, okay, the rotational constant changes, it's a number, right? We compare with it and we see like it works or not. With electron bubbles, it's absolutely true. They works where they expanded in angular momentum, and if this interacts with the bulk of helium, they're going to exchange the angular momentum.
If you consider that extend the thickness for the many angular gas, this is just the case.
Yeah, but even for single ones, the question is like, what is the measurable, right? And the measurable would be like, you measure the spectrum of these electron bubbles, right? The electronic spectrum. But the problem is that you cannot measure the spectrum in helium and compare it with the free electron bubble, right? And this is challenging. So like if you're aware of any data where, you could just see the change of like in helium, out of helium or something of that sort, would greatly appreciate it. But we were not able to find much to compare with, but the theory could work, yeah. Oh, this is an excellent question. There would be a difference. There is a huge difference. There is a huge difference because in optics, you're pretty much restricted to the dipole approximation, right? So you have angular momentum 1. Like in phonons, it depends on the symmetry. So for example, like if you take a molecule which is non-polar, right? But super long, right? There will be no angular momentum 1, but there will be angular momentum 2. And it will be very large. Actually, for most molecules, angular momentum 2 is dominating the quadrupole contribution. And it depends on the symmetry of the molecule because it's not, it's not just electromagnetic wave, right? It depends on the microscopic coupling between the molecule and the buzz, which can be almost anything. No, there are selection rules, but it depends on a particular molecule. So usually, like quadrupole interactions are dominant. Usually, I would say that.